Haven't we all wished at some point that we could predict the future? Things like forecasting next quarter's sales or figuring out how many people are going to fly next summer. This desire to know what's coming is totally universal. And it turns out we actually have some really powerful ways to do it, just by listening to the patterns of the past. So let's dive in. So that's the big question, right? How do we do it? And spoiler alert, it's not about a crystal ball. It's about statistics. We're going to dig into a foundational method that helps us really listen to what our data is trying to tell us about where it's going next. Okay, so this right here is our puzzle. It's a famous data set of airline passengers. And when you look at it, two things probably jump right out. First, there's that steady upward trend over the years. And second, you see those sharp spikes that happen like clockwork every single summer. Our mission, then, is to build a model that can actually understand this pattern and predict what's coming next. To solve this puzzle, we're going to turn to one of the most trusted and powerful tools in any forecaster's toolkit. And that tool is called ARIMA. It's a total powerhouse of a model. It's been a cornerstone of this field for decades, and for good reason. It's flexible, you can understand what it's doing, and it's just incredibly effective. Now, I know what you might be thinking. That acronym, ARIMA, it sounds a little intimidating, right? But don't worry. We're going to break it down piece by piece into really simple, easy-to-understand ideas. So, at its heart, an ARIMA model looks at two main things to make a prediction. First, it looks at its own history, its past values. And second, it looks at the mistakes it made in its past predictions. That's really it. It's a surprisingly simple and intuitive idea. So let's start with the AR part. That stands for autoregressive. All this really means is that the model assumes that what happens tomorrow is probably related to what happened today and yesterday and the day before. It's basically forecasting by looking in the rearview mirror. Next up is the I for integrated. Now, this is the secret sauce for dealing with trends. Instead of modeling the actual number of passengers, it models the change from one month to the next. This little trick is called differencing, and it's like a magic wand that removes the trend and makes the underlying patterns way easier for the model to see. And you can see that transformation right here. On the left, there's our original data, climbing steadily up. But on the right, after we apply differencing, poof, that upward trend is totally gone. The data is now just hovering around a stable level. We call this stationary, and this is exactly what our model needs to do its job. And finally, we have MA for moving average. Now, this part is really clever. It looks at the errors from its previous forecasts, the surprises or shocks, and it uses that information to adjust what it's going to predict next. It's kind of like correcting your aim after each shot to get closer and closer to the target. So we have our building blocks, AR, I, and MA. But how do we know how much of each ingredient to use? Well, that brings us to the actual process of building the model. Data scientists follow this classic three-step recipe called the Box-Jenkins methodology. First, you identify the right kind of model. Second, you estimate it, which means fitting it to the data. And third, you do some diagnostic checking to make sure the model is actually any good. It's a system: identify, estimate, and check. That first step, identification, is basically detective work. And these two charts, the ACF and PACF, these are our biggest clues. The patterns you see here, in these bars, tell a story about the data's hidden patterns. And by reading that story, we can figure out exactly how many AR and MA parts we need in our model's recipe. And here's a really important pro tip in model building. Keep things simple. When you're checking your model, you look at every little piece, and if a piece isn't really pulling its weight statistically, you just take it out. The goal is always to find the simplest possible model that still does a great job predicting. Here's another cool diagnostic check. I know this plot looks complicated, but the rule is incredibly simple. See that big circle? For our model to be stable and reliable, all those little dots just have to be inside it. It's a quick pass-fail test. And since ours are, we get a green light, our model is good to go. Okay, so our model is stable. That's great. But what about those yearly spikes we kept seeing? That's seasonality, and it's a super common pattern you find in real-world data. To handle this, we use a special version of our model called SARIMA. And yep, the S stands for seasonal. This chart shows you exactly how it works. On top, you've got the trend and the seasonal spikes. In the middle, we've used differencing to remove the trend, but the spikes are still there. But look at the bottom.
We apply seasonal differencing, which basically compares this July to last July, and the spikes are gone too. Now the data is totally stable, and our model can learn from it. This is so crucial for a business trying to predict, say, holiday sales.
Now, all that detective work with the charts, I know it sounds like a lot of effort, right? Well, the good news is that these days, a lot of this process has gotten much, much easier. We now have automated tools, usually called something like auto ARIMA. So instead of a data scientist manually staring at those plots, an algorithm can just search through hundreds of different model combinations and pick the best one automatically. Of course, this doesn't replace human expertise, but it definitely speeds things up. A lot. And how does it pick the best one? It usually uses a score, like the Akake Information Criterion, or AIC. The AIC is awesome because it's all about finding a balance. It wants a model that's accurate, but it also penalizes a model for being too complex. This helps stop the model from learning the random noise in the data instead of the real underlying pattern. What's really cool is just how flexible this whole ARIMA framework is. A lot of other common forecasting models are actually just special, simplified cases of it. That simple random walk forecast, that's just an ARIMA model. Simple exponential smoothing, yep, that's an ARIMA model too. It's this amazing, unifying framework for so much of time series analysis. So if there's one thing to take away from all this, it's this. ARIMA isn't just a single model. It's a whole framework for understanding and forecasting data over time. It's powerful, you can actually explain it, and it absolutely remains a fundamental tool for any data scientist. And that brings us to this great piece of wisdom. The whole idea here isn't just blind prediction. It's about building a model that first proves it has a deep, statistical understanding of the past. Only then should you trust it to tell you anything about the future. Which leaves us with a final, really important question. In this age of super complex AI and neural networks, why do we still rely so much on a statistical model that was developed back in the 1970s? Well, the answer is in its simplicity, its ability to be interpreted, and its proven rock-solid performance. It just reminds us that sometimes the most elegant solution is the one that has truly stood the test of time.